A silent catastrophe is unfolding inside enterprise software networks. Two autonomous artificial intelligence systems, programmed to manage a corporate supply chain, have locked themselves in a loop of polite, endless disagreement. Within 45 minutes, they consume $6,000 in server fees, corrupt a customer database, and shut down a shipping terminal. This is the reality of vibe coding. When we let AI agents simply talk to each other, things do not get smarter. They break. For the past few years, the tech world was obsessed with a simple promise. If one AI model is smart, then 10 AI models chatting with each other in natural language must be brilliant. We envisioned digital offices where virtual researchers, writers, and managers collaborated in real time. But by mid-2026, the engineering community hit a hard wall. This naive approach, often called vibe coding, has failed in production. In the real world, natural language is a terrible medium for system architecture. It is imprecise, expensive, and slow. When you chain multiple language models together without strict boundaries, you encounter a phenomenon known as hallucination compounding. If the first agent makes a tiny, unnoticed mistake, the second agent accepts it as absolute truth, amplifies it, and passes it to the third. By the end of the chain, the final output is completely toxic, and finding the original error is nearly impossible. To understand why this happens, we have to look back to 1966, to one of the most famous unfinished art projects in history. Brian Wilson of the Beach Boys was trying to record the album Smile. Instead of writing songs from start to finish, Wilson pioneered a highly modular approach. He recorded hundreds of tiny, brilliant fragments of music, distinct modules of sound, planning to stitch them together later. But without a rigid, master blueprint to guide the arrangement, the project collapsed under its own weight. The brilliant fragments remained just that, fragments, scattered across shelves of magnetic tape. This is exactly what happens when you build an AI system using only prompts. Each prompt is a brilliant, modular fragment of capability. But without a deterministic orchestrator, a master score to dictate exactly when and how each fragment plays, you do not get a masterpiece. You get expensive noise. The solution to this chaos is not a secret. It is a fundamental principle of classical computer science. Back in 2013, developers were solving a very similar problem with decentralized web services. They realized that when you have dozens of independent microservices handling data, you cannot just let them talk to each other at random. You need structured, data flow orchestration. Today, the AI industry is undergoing the exact same realization. We are moving away from letting language models dictate the flow of a program. Instead, we are building rigid, code-first pipelines. In these modern architectures, the language model is not the boss. It is merely a utility. The master structure of the workflow is written in traditional, deterministic code, like a state machine, which dictates exactly what can happen next. The AI is only called upon to perform specific, isolated tasks within those strict boundaries. This shift has birthed a new paradigm called Skele-Code. Developed to bridge the gap between human subject matter experts and automated code execution, Skele-Code completely flips the traditional agent model on its head. In a typical agent setup, the AI runs the loop, constantly calling itself to figure out the next step, which drains your budget and introduces endless points of failure. In the Skele-Code approach, the AI is restricted to writing the static code structure, the skeleton of the workflow. Once that skeleton is generated, the AI steps completely out of the way. The actual execution of the task is handled by a standard, deterministic computer program. If an error occurs, the system does not ask the AI what to do next. It simply hands the specific error log to the AI, asks for a quick patch, and returns to the rigid execution line. This approach slashes token costs by orders of magnitude because you are no longer paying a frontier model to make basic routing decisions that a simple line of Python could handle for free. But what happens when a workflow is too complex for a static, rigid script? What if the system needs to handle highly dynamic, unpredictable queries, like searching through millions of unstructured corporate documents? This is where researchers are introducing experimental frameworks like HERA, which stands for Hierarchical Evolving Agentic RAG. Instead of using a static set of rules, HERA uses a layered architecture. At the bottom, You have specialized agents designed to retrieve and filter data. At the top sits a master orchestrator. This orchestrator does not just blindly pass data along. It tracks the success and failure of previous runs. If a specific retrieval pathway fails to answer a user's question, the orchestrator dynamically adjusts the prompts and strategies of the lower-level agents for the next attempt. It is a system that learns and evolves its own internal routing pathways over time, combining the flexibility of AI with the structural safety of a hierarchical organization. Even with the best orchestration, things can still go wrong. And when an AI system fails in a massive corporate environment, you cannot just hope for the best. You need to know exactly why it failed. This has led to the development of provenance tracking tools like prov-agent. Think of this as a black box flight recorder for AI workflows. In a complex, multi-agent system, prov-agent records a unified paper trail of every single interaction, every tool call, every prompt modification, and every hallucination. If a financial report generated by an AI pipeline contains a fabricated number, developers do not have to guess where it came from. They can run a forensic analysis backward through the provenance graph, tracing the corrupted data directly to the exact millisecond and the exact agent that generated it. This level of traceability is what finally makes AI systems safe enough for regulated industries like medicine, finance, and aerospace. The great irony of the modern AI boom is that the most capable systems we are building are not the ones with the most freedom. The future of enterprise AI is not wild, conversational agents running unchecked across databases. The future belongs to highly restricted, deeply engineered, deterministic state machines. We are realizing that language models are not digital employees. They are incredibly powerful, highly volatile gears. And to make a machine run smoothly, you do not let the gears decide where they want to spin. You build a rigid, classical frame to hold them in place. Only then, when bound by the strict laws of traditional software engineering, can these systems finally deliver on their promise.